An important property of alkenes is that the double bond in the center of the molecule in this example is non-rotatable. Why is it non-rotatable? Well, let's take a crude drawing real quick of our alkene, and we're going to draw in the hydrogens, the substituents, and we're going to draw in the p orbitals that will overlap in our alkene. So these p orbitals have an overlap, which causes our pi bond to form. Now if we rotate along this bond, what we're going to do is we're going to move these p orbitals out of plane with each other, which means we would end up breaking the bond. So at room temperature, alkenes are non-rotatable. We would have to break that bond to rotate them. Because alkene bonds are non-rotatable, we have stereochemistry. These two molecules that we've drawn are different. If we can't rotate this bond around, then this methyl group and this methyl group are on opposite sides of the alkene. We would call this trans. In the other example, this methyl group and this methyl group are on the same side of the alkene. This would be cis. So if we were to name these molecules, we could say that these are both 2-butenes, but one of them is trans 2-butene, the other one is cis 2-butene. It turns out that cis and trans aren't always appropriate. So let me give you an example. In this case, we have a methyl group, a chlorine, a bromine, and an ethyl group. Notice the position of the bromine and the ethyl group here change. If we were going to use cis or trans, you should remember that we have to have two identical substituents on either side. So if we had two chlorines, one on the left, one on the right, we could use cis or trans. In this example, we can't do that. Instead, what we will designate these as either E, where the largest substituents are on the opposite side, or Z, where the largest substituents are on the same side. So let's do a simpler example before we get to this larger one, with our cis and trans 2-butene. So in this case, let's draw in our hydrogens. Our hydrogens are the smallest. They're going to be the lowest priority. So if we're looking at this carbon on the left, the highest priority is the methyl group. If we're looking at this carbon on the right, the highest priority is the methyl group. Notice they're on opposite sides of the alkene. So this example will be E. So we could name this E 2-butene. In the other example, again, let's draw our hydrogens. Notice they're pointing in the same direction. If we're going to assign the highest priority, we have 1 and 1, which are on the same side, so this will be Z. So this example is Z 2-butene. Now let's go back to the example on the left with the chlorines and the bromines. Let's take a look at the leftmost carbon. Chlorine has the largest molecular weight. It's going to be our highest priority. Bromine on the right has the highest molecular weight, so it will have the highest priority. Notice these are on the opposite face, so this will be E. In the other example, chlorine is number 1, bromine is number 1. This will be an example of a Z alkene. So let's apply this naming to a larger molecule that you've seen before. First, let's go ahead and assign the longest chain. 3, 4, 5, 6, 7, 8, 9. Take note that the 4 is the lowest substituent. That's where the alkene begins, right here. So this is 4-nonene. Next, we're going to assign the substituents. We have a 6-chloro group and an 8-methyl group. So this is 6-chloro, 8-methyl, not 4-nonene. Now we need to assign the stereochemistry. So we have two stereocenters here. We have the alkene stereocenter and the chlorine stereocenter. The chlorine we did before. This is 1, 2, 3. Counterclockwise. The chlorine is back, so this will be R. The alkene, if we take a look, the bottom carbon has the substituent coming off to the right. That's number 1. The top carbon has the substituent coming off to the left, so this is opposite. This will be E. If we're going to add this to the name, we're going to do it numerically, so this is 4E, 6R, and then we put the rest of the name. 6-chloro, 8-methyl, 4-nonene.